I'll hand this back today. Just take a look at the key here. So the Kb chemical reaction, it's Kb is base plus water, Ka is acid plus water. This is an acid-base reaction. Water being amphoteric, it goes either way. And so here we have the base plus water, which yields ammonium hydroxide. And so this is the equation I was looking for here. It's the chemical reaction. Acids, you could do acid ionization, but for bases, we have to do hydrolysis reactions. Ammonia doesn't ionize itself necessarily. Although it does have a Ka where it collides with water to form amide, that's possible too. For problem number 20, I was looking for, in step 1, that, I was looking to see if you recognize K is very large. K is very large, then that goes to completion. For step 2, I accidentally wrote Ka2 of a .021 rather than a .011, or 2.1 times 10 minus 2. But either way, I just went through the calculation, so it didn't matter which one you used, just as long as the setup is correct. And so I was looking, did you carry the products from step 1 down? Some people carried the bisulfate down, but they didn't carry the hydronium. You have to carry both down. Those are common species between step 1 and step 2. Then we set it up. It looks like this would be a good candidate, possibly, for the simplifying assumption, but the simplifying assumption fails. It's 11% change. 11% change is too big. And so we have to get it into quadratic form, which I did here. And then I just used the quadratic solver for this. But that gives us a different x value, And we plug that x value back in here, get the equilibrium concentrations, and then double check the K. And the K checks out. It's 0.011. Okay. And then I was looking, because I asked for the inventory of all species, I wanted the hydroxide in there as well. So step 3, which is Kw, Kw is not going to add that much more hydronium. In fact, we expected to add a negligible amount of hydronium, but it would add a significant amount of hydroxide. So it came out to 9.16 times 10 to the minus 14 molar hydroxide. And so I was looking for 3 steps there. And then I'm summarizing it. These are the concentrations I end up getting here. Pass it back. I'll pass it back a little bit later. For number 21, some people just did step 1 here with the HCN. When you look at it, it's 10 to the minus 5 molar. 10 to the minus 5 molar, that means it's kind of dilute. And so water, Kw, may or may not. The most Kw is going to add is like 10 to the minus 7, 10 to the minus 8, 10 to the minus 9, a small number. And so let's say, it can't be 10 to the minus 7, that would be too high, but let's say it was like 10 to the minus 9, then it may be significant, maybe not. It's borderline, so the only way you can tell is actually do the calculation. Since this is a homework problem, if you didn't do the calculation to show that Kw is significant, and skipped it and went straight to simultaneous, that was okay too. So anyway, we did the step 1 here. And so some people got a pH, just doing step 1, it's a very low hydronium concentration. So you get a pH of 7.10. But 7.10 is acidic or basic? It's basic. And HCN is hydrocyanic acid. So is hydrocyanic acid a base? we call it hydrocyanic base? No. And so if you get a pH of greater than 7, then there's something wrong. The pH should be less than 7 for an acid solution. And so what's wrong is we're not looking at the hydronium contribution of water. And so when we look at the hydronium ion contribution of water, it turns out it's pretty significant. So I try with water, and I do the assay. The assay fails. So you got hit with 2 quadratics here. But I just use my quadratic solver. 6.18. The assay failed with 161%. That's what I calculated. You should double check that calculation. But using the quadratic, we get this for the hydronium. The hydronium started at 787 from the hydrocyanic acid, but the water added 6.8. So we almost doubled the amount of hydronium by factoring in water. So we started out with 7 and ended up at 14 here. And so essentially doubled it, 15. And so KW turned out to be a significant contributor of hydronium, ending up doubling it. But the problem is I do this myself. I notice a lot of people don't do this, but you might consider doing this, is checking your equilibrium concentration. And so we calculate these equilibrium concentrations, we plug these back into K and C. And this one checks out. It's okay. 6.24, 9 times 10 minus 10, it should be 6.2. So it's off a little bit. But it still rounds to 6.2 times 10 minus 10. So we're okay. However, if we double the hydronium, are we still going to be okay? Now, if we double the hydronium, then essentially we're going to be, that's going to have a 4-fold impact, because it's going to be, a 2-fold impact. It's not squared, it's just here. And so that would kind of double our K value. If we double our K value, is it still going to be okay? So rather than having a 6.2, we had a 12.4. Is that going to be close enough to 6.2? No. And so it's important that you recognize that this is a case where step 2 perturbs step 1. And when step 2 perturbs step 1, what do? It's simultaneous. So it's a significant change in hydronium, and that's going to perturb, therefore, simultaneous. And so you can set it up for simultaneous. Here, we'll do HCN. So if you did this, set up the ice tables here, and then you set up we have 2 unknowns, so we need 2 equations. So you set up the 2 equations, and you don't solve these 2 equations for the 2 unknowns. You would have gotten full credit up to this point, 7 points. If you went beyond this, then I gave you extra points. And if you solved it completely, I gave 3 extra bonus points. And so that makes a total of 7 bonus points on this test. This test is worth 50. So what you'll do is you'll take your multiple choice, the number at the bottom, and multiply that by 2, and then add what you got for the free response here, and that gives you your total for this test. I should have handed this back earlier, but since people come in. Before I do that, probably should, well, the curve that you generated, you're either going to have a monoprotic acid you can tell a monoprotic because it's going to stay flat and there's going to be one steep rise. and then it'll flatten out again. Versus a diprotic acid. A diprotic acid is going to have a small blip at the midway point and then a large one at the equivalence point. And so there are going to be two waves here. And this is plotting pH versus milliliters of sodium hydroxide. And we just call this the titration curve. So we can generate this experimentally. We just need to pay attention to collecting enough data. You know, how many data points define this line? So when we make the plot, we want to show how many data points are defining this. By showing the individual data points here. All right, so there are different kinds of titrations. Titration types. We have the first type, which would be a strong acid plus a strong base. When we have a strong acid, strong base combination, we start off at quite low pHs. You know, the pHs are going to be around 0, 1, somewhere around there. So the initial pH is usually quite low, let's say about 1 here, depending on the concentration. And then it rises up and then flattens out. And then we'll have a steep rise here near the equivalence point. And this steep rise is usually defined by a jump in pH units. This is a big jump. A big jump would be like 6 plus, you know, delta pH. So about plus 6 pH units. It's not a good color. They say 6 to 8. Say 6 to 8. And so there are different regions that we calculate on the curve to figure out the pH. This first region here is just acid and water. And so this is just a Ka calculation. And when we have pHs this low, do we worry about Kw? No. When you have that much hydronium, Kw is not that significant. Okay, then we're going to have this region here between the initial and the equivalence point. In between the initial and the equivalence point, this part of the curve here is called the excess acid region. And so if we do an example of this, it would be like HCl and sodium hydroxide would be an example. And in the excess acid region, well, actually the initial, so normally we want to calculate some points. So we'll calculate the initial pH. This is Ka. And then we go into the excess acid region. In the excess acid region, we like to do ice tables like this. So we'll have sodium hydroxide, and sodium hydroxide is going to be our limiting reagent, Lr here. And then what we're going to form from this is we're going to form salt and water, you know, sodium chloride and H2O. So for example, here we start off with our initial HCl and our initial sodium hydroxide. And then we have 0 for the sodium chloride. And this is concentration, so H2O is up here liquid, so we'll ignore it. And then what we're going to do is we're going to consume all of the sodium hydroxide. And so I'm going to use this. The concentration, because it's a 1-to-1 mole ratio, I can do it this way. So the molarity of HCl I'm going to lose is equal to the molarity of the sodium hydroxide initial here, because we're going to lose that over here as our limiting reagent. So at the end of this, I'm going to have the HCl initial minus the sodium hydroxide initial. And this is going to be the equilibrium concentration of the HCl. And then for the sodium hydroxide, I'm going to have nothing left over. And for the sodium chloride, I'm going to have plus the sodium hydroxide initial. And so the concentration of sodium chloride will be equal to the concentration of sodium hydroxide initial. And water is pure liquid. And so we do these to keep track of the molarities here. Okay, and then this is step 1. In step 2, we look at what we have left over. In step 2, we have the acid plus neutral salt. Actually, this is a common ion problem here, but it's a special one in which the conjugate base of the acid is too weak to be considered as acidic. And so this is a conjugate pair, but it's not equal to a buffer. It's not equal to a buffer because in order to be a buffer, we need the conjugate pair to be weak, both weak. In this case, the conjugate pair, one's strong, the other's weak. So this is not a buffer. In other words, the way we would look at this is a strong acid and neutral salt. Plus neutral salt. And so the strong acid, neutral salt we don't really care about. We're only interested in pH. So we'll just do the Ka for the strong acid. So titration problems are going to work like this. After you're past this initial point, we're always going to have a step 1. The step 1 is going to be the strongest acid plus the strongest base. And then we look at what's left over at step 2. What's left over at step 2 is where we're going to get our pH. And so we'll do the reaction first, see what's left over, and then set that up accordingly. And so here I just set up another ice table with Ka. All right, so as we get closer and closer to the equivalence point, we have less and less strong acid, excess strong acid. And pretty soon, we have so little strong acid that the pH is not really determined by the strong acid. The pH is really determined by what? By the water. And so here, what we would do in the particular case is, let me do this in green here. When I look down here, step 2 is okay. However, when I get here and I look at step 2, step 2 is still excess acid, but we have so little excess acid that the concentration is going to be very small. If the concentration is very small, then we have to do Ka, and then we have to do a step 3 because we have so little hydronium generated from step 2 that we have to go on to step 3, which is what? If there's so little excess acid that the concentration is very small, let's say I had 10 to the minus 8 molar HCl left, I wouldn't want to stop there because 10 to the minus 8 molar HCl would give me a pH of 8. Is pH of 8 reasonable for an acid? No, and that means most of the hydronium comes from water. And so we have to do a step 3 here, Kw. Whereas down in this yellow region here, we don't have to worry about Kw. It's just when we get close to what's called the equivalence point. Okay, that which brings us to the next part of the curve here, and that's going to be the equivalence point here. And so near the equivalence point, we're going to be using kW. At the equivalence point, that's all there is, because in this particular case, at the equivalence point, we've neutralized all of our acid. So let's talk about that here. This is the equivalence point. We have equal amounts of HCl and sodium hydroxide. And this is going to produce salt, sodium chloride, and water. H2O liquid. So initially we start off with equal amounts, and then it's going to react stoichiometric. In other words, we have stoichiometric quantities. So what we're going to have is we're going to have no limiting, no excess reagent. Being stoichiometric, it's going to end up at 0 and 0. And so the initial of the HCl is equal to the initial sodium hydroxide, which is going to equal the equilibrium of sodium chloride. And so I'm not going to fill out the whole table. I'll just fill out these parts here. And so what we have is we just have a neutral salt and water. If it's a neutral salt, then all there is Kw. If all there is Kw only, then pH is 7.00. So when we have a strong acid and a strong base, the equivalence point comes out a pH of 7.00. Here. And we know we've neutralized all our acid when we hit pH 7. Okay, after the equivalence point, then we have excess base. And so this would be the excess base region here. So if we go to the excess base region, our step 1 is going to be the same. The step 1 is just going to be the strongest acid, HCl, plus the strongest base, sodium hydroxide. And this gives us sodium chloride plus water. Now we have excess base. So that means the HCl must be our limiting reagent here. And that means my initial HCl concentration must be less than my initial sodium hydroxide. So I have more sodium hydroxide than HCl. And therefore, I'm going to run out of HCl in this. If I run out of HCl, I'm going to end up at 0 molar HCl. And then I'm going to end up at sodium hydroxide initial minus HCl initial left over base. Now, if the two concentrations are equal, then I'm at the equivalence point back there. And so this was 0. And then how much sodium chloride am I going to generate from this? I'm going to generate the limiting reagent's worth. And so the sodium chloride will be equivalent to the sodium hydroxide initial concentration. So these are all initial concentrations here. Okay, so that's step 1. And then step 2. Step 2 is Kb of hydroxide, but Kb of hydroxide is just equal to the hydroxide ion concentration, essentially. Because when hydroxide hydrolyzes water, what forms? The HCl, yeah, you're right, sorry. I made a mistake with that. Sorry, correct this. This has to be the HCl. That's right. Initial concentration. So this step 2 is kind of easy. It's just hydroxide and water makes water and hydroxide. So really nothing happens. So we kind of skip this. And so just whatever hydroxide you end up with, and sodium hydroxide is a strong electrolyte, so that's going to tell you that. All right, and then what we're going to get from this is we're going to get the POH, and then we convert that to pH. So the sodium hydroxide is going to supply it, the hydroxide, especially, when you get to high pHs here, pH 9, 10, 11, 12, when you get those high pHs, we get a lot of hydroxide from the excess base. However, if we're in this region, then we just have a minuscule amount of hydroxide. If you have a minuscule amount of hydroxide, then we have to worry about what? We have to worry about anybody know? Let's say you had like 10 to the minus 8 molar. You have 10 to the minus 8 molar hydroxide. 10 to the minus 8 molar, the power is 8. And so that gives you a POH of 8. A POH of 8 means the pH is 6. Can an excess sodium hydroxide solution have a pH of 6? That's impossible, because a pH of 6 is not basic. A pH of 6 is acidic. So what am I missing? Well, I'll tell you what I'm missing. I'm missing KW. And so step 2 is just going to be the hydroxide. And then step 3 is we're going to see how much additional hydroxide we're going to get from KW. So KW will produce it. And that's just in the regions near pH 7 here. As we get higher and higher, it becomes less and less important to do it. It's just super dilute here. And so in the excess acid region, we have a minuscule amount of excess acid. In the excess base region, we have a minuscule amount of excess base. And so the type of calculation you do just depends on what part of the titration curve you're in. Here. So strong acid, strong base is a common titration. Another common type of titration is the weak acid, strong base. And that's what you guys did. Weak acid, strong base. So let's take a look at monoprotic here first. Number one, the pHs start off a little higher, not 0, 1, 2, but more like 2, 3. pHs start off a little bit higher. 2, 3 range. And we go up. And then there's going to be a steep rise here. And then it flattens out here. So we could take a look at the different regions here. So here the initial is just going to be Ka for the acid. Maybe Ka, no, actually just Ka. Yes. In between the initial point and the equivalence point here, which is the inflection of the curve, we have the excess what region? We have the excess acid region. We have to worry when when it becomes so dilute, the amount of excess acid becomes extremely dilute. Then in these regions, like close to the equivalence point, we may worry about KW more. All right, so our acid in this case is just going to be a generic acid, weak acid HA. So if we're in the excess acid region, then we're going to have HA, our generic weak acid, reacting with a strong base. I'll just use a specific strong base, sodium hydroxide. And this is going to make our salt, sodium A plus water, H2O liquid. And so initial, I'm going to have excess acid. And therefore, the sodium hydroxide is my limiting reagent. And the sodium acetate is 0. And the change is going to be complete. Let me talk about this. There's a rule which we're going to follow. And the rule is strong, react to completion. Let me give you some examples here. Let's take a strong acid, HCl, and react it with water. What's the K for this? You should know. The strong acid plus water is going to give you a K value of very large. Is water a very strong base? No, water is one of the weaker bases. What if we take HCl and react it with a stronger base? Like ammonia, something like that. Do you expect K to be the same size, bigger, or smaller when we react it with a stronger base than water? The same? It turns out it's not the same. When you react it with a stronger is more reactive. And so I'm going to call this K very, very large. It should be bigger than reacting with water. When you take a strong acid like this and react it with a strong base like sodium hydroxide, what's the K? Is it going to be bigger? Yes, it's going to be bigger. It's going to be very, very, very large. And so I have three very larges. I have the very large, Ka, Kb. I have the very, very large when a strong acid reacts with a weak base or a strong base reacts with a weak acid. You know, to be vice versa. And then I have the triple V large, the strong acid and strong base. So here we have the double V. So we have HA and sodium hydroxide. Sodium hydroxide is much better. What did I have up here? I had HCl and sodium hydroxide. That's strong, strong. If I have strong, strong, how big is my K? my K is going to be very, very, very large here. Now, if I go down to weak acid plus sodium hydroxide, this is going to be K, which is going to be very, very large. Here. And so this is going to go to completion. So that means I'm going to consume the entire limiting reagent, and the excess acid that's left over will be HA initial minus the sodium hydroxide initial. And the amount of sodium A I'm going to get is going to be equal to the limiting reagent, which is going to be sodium hydroxide initial. This is step one. When we look at the products of step one, what do you see? What I see is I see weak acid. And I see a weak base. When we have a weak acid, weak base combination, do you know what we call that? A weak acid plus a weak base we call a buffer. I'll talk about how buffers work. Since these are conjugates of one another, then we call this a special type of buffer. We call this the Henderson-Hasselbalch buffer. If we do the Henderson-Hasselbalch buffer, then that means we can do the Henderson-Hasselbalch equation. And so the Henderson-Hasselbalch equation, we have two forms for. We have the Ka form and we have the Kb form of the Henderson-Hasselbalch equation. The Ka form is that the pH is equal to the pKa plus the log of base over acid initial. This is initial for step 2 here. The Kb form is that the pOH is equal to the pKb of the base form plus the log of the acid initial over the base initial. Do I have to do both forms, the pH and the pOH form? The answer is no, because they describe the same equilibrium, correct? And the only difference is one describes the equilibrium in terms of pH, the other describes it in terms of pOH. So you know which form most people use? Most people use the pH form because that saves us one calculation, converting pOH to pH. However, I noticed that your books in the homework, they're having you use the pOH form too. So both forms. And sometimes it makes sense to use the pOH form if the base is more common than its conjugate acid. All right, so we'll stick with this form. So this is just equal to the pKa plus the log of, now these final concentrations in step 1 will become the initial concentrations in step 2. So this is going to just be the log of the sodium hydroxide initial over the HA initial minus the sodium hydroxide initial. All right, then the next point on this titration curve is what we call the equivalence point here, except it's different than the previous equivalence point. Because at the equivalence point, we're going to have this. We're going to have equal amounts, in other words, stoichiometric amounts of HA and sodium hydroxide. And so at the equivalence point, these two are equal. And there's no limiting, there's no excess. And we end up with the same. So what we end up with is NaA. We end up with the basic salt. And so step 2 is just going to be Kb for the basic salt. If it's a basic salt, the pH can't equal 7. And so the equivalence point, we're going to have a basic salt in step 2. And therefore we're going to produce hydroxide, and therefore the pH is going to be greater than 7. And then after the equivalence point, then we have the excess base region. Plus basic salt. So the excess base, sodium hydroxide, is going to contribute the most hydroxide to it, which is going to ramp up the pH. And then the basic salt will produce some additional hydroxide, unless we're very close to the equivalence point. If we're very close to the equivalence point, then it's probably the basic salt that's providing most of the hydroxide, or even Kw, which is providing most of the hydroxide. So near the equivalence point, we have to do more. To determine it. There's shortcut ways of doing this. And so I'm going to show you the long way, and I'm going to show you the short way in titration calculations. So let's do some example titration calculations here. And so normally, if I want to draw the curve, at least get the general shape of the curve here. Am I going to calculate hundreds of points? Yeah, I'd like to calculate hundreds of points, but this is going to take way too much time. So what I'm going to do is I'm just going to calculate a few points that I like to calculate. I like to calculate the initial pH. And so this is 1, the initial pH. And then I'd like to calculate, okay, if this is the equivalence point here, then I'd like to calculate what we call the half equivalence point here. I want to know what the pH is at the half equivalence point. And so usually that's my second calculation there. And then to get some of this flat region here, I'd like to calculate You know, at least 2, maybe 4 more points in that region. And so the ones I like to do are like the 1/4 equivalence point. And the 3/4 equivalence point. And then I like to do the 1/11 equivalence point. One-11th equivalence point. And I like to do the 10/11 equivalence point. So the equivalence point is going to be the 4 out of 4 or the 11 out of 11. That would be the full equivalence point here. The 4/4 or the 11th. And those will be good. I also like to calculate the equivalence points here. And so let's see, I do 2, maybe 3, maybe 4, you know, either of those. And then 5, we'll do this one. And then 6, we'll do something out here, maybe, in the excess base region. Now, there are 2 types of calculations that we do. 2 types of calcs. We aren't going to do these for your titration curves because your titration curves were determined experimentally, except for one, but that calculation is quite easy. So what are the 2 types of calcs? The 2 types of calcs are you're given the milliliters of sodium hydroxide, then you have to determine the pH. That's one. The other type of calc is when you're given the pH and you have to determine how many milliliters of sodium hydroxide it took to get to that pH. That's calc 2. So we'll just do an example here. The example is going to be a titration in which we're going to titrate a sample of acetic acid. So we'll go with 0.100 molar acetic acid. And then we're going to titrate this with, I'm going to keep the numbers simple, 0.100 molar sodium hydroxide. And so at 0 milliliters, then we just have acetic acid, 0.100 molar acetic acid. So it's just an Ka. And so we'll have acetic acid plus water. This is going to give us hydronium plus acetate. The Ka value for this we could look up in the book. It's 1.8 times 10 to the minus 5. And so the initial is 0.100, water, 0, and 0. And there's going to be a change. The equilibrium, I'm going to have 0.100 minus x, and x molar. And so Ka is equal to x squared over 0.100 minus x. And then we use the simplifying assumption. It's just going to be x squared over 0.100 and solve for x, which comes out to 0.001334, which is a 1.3% change, and so it's okay. So we're just interested in the pH, so I'm going to plug that in over here, 0.0134 molar for the hydronium. And then for the pH, well, even though we're only interested in the pH, I'd probably calculate the rest of these. The reason I'd calculate the rest of these is just to make sure I didn't make an error. And so I probably want to do that. 0.0134 molar, and this is going to be 0.09866 molar. And so we'll just do a K check here, just to make sure it's okay. And checking the K, I'm going to go 0.0134. This calculator. From my other calculator. 0.0134 squared divided by 0.09866. 1.819. So my K comes out to 1.819 times 10 to the minus 5. It should be 1.8. It's off a bit, but then, you know, I'm using the SA. So this is probably good enough. 1.8 times 10 to the minus 5, rounded. All right, so the pH is going to equal the negative log of the hydronium. Now, I have to worry. Do you think Kw will contribute much to this? Should I not quite do this? Maybe I should add the hydronium from Kw, right? But do you think it'll contribute much to this? This is 10 to the minus 2. No. If my initial is 10 to the minus 2, I don't think it's going to contribute much at all. And so I'm going to stop here and assume that the hydronium additional that we get from Kw is negligible. And so let me just take the log of 0.0134. And I get a pH of 187. 1.87. I'm allowed 2 sig figs, so I'm going to carry 1 extra. So the 1 is not significant in a power function. It's just what's ever after the decimal. So I'm showing 3, but this third one I'm not allowed. I'm just showing what it is. And so it comes out to 187. So when I'm mapping out the titration curve, I calculated the first point. The first point is the initial pH. The initial pH is a pH of 1.87. Okay, then I'm going to go to my half equivalence point. That's going to be my next calculation. But I have to determine what is my half equivalence point. And so it depends on how many milliliters I have. So let's say I'm going to go with, how many milliliters of acid do you usually get? 25 milliliters? 20 milliliters? Well, I'm going to go with 20 milliliters here, 20.00 milliliters. If I have 20.00 milliliters of 0.100 molar acetic acid, how many milliliters of sodium hydroxide is it going to take to neutralize it? And so this is easy. This you should be able to do in your head because they're the same concentration. And so how many milliliters? If I have 20 milliliters of acid, I'm going to need 20 milliliters of base to get to the equivalence point. So I have to do that calculation. Sometimes in the homework the numbers aren't so clean. So they make you actually do a calculation. So sometimes they'll give you 0.175 and some 0.250, you know, some odd numbers. And then it's not so easy. You'll have to figure out the ratio, like Chem 1A. And so the half equivalence point is going to come in at 10 milliliters. And the full equivalence point is going to come in at 20 milliliters. So we're going to do the half equivalence point calculation in two ways. We're going to do it the long way and the short way. Okay, once we get into the titration, then there's one more step that I need to talk about. And this is either you're going to have to do one step at the beginning or one step at the end. The book likes to do the one step at the end. And so what the book does is, we've been using concentrations all along, but the book is going to switch to moles. In fact, the book is going to switch to millimoles because we aren't using that many moles. And so the book likes to write the ice table in terms of moles or millimoles. And then at the end, reconvert those all to molarities so that you can figure out what the equilibrium concentrations are. But what I like to do is I don't like to do it at the end. I like to do it at the beginning, even though the numbers might not come out as clean. But I don't care which way you do it. If you want to use millimoles, that's fine. I'm going to continue using molarity. The problem with using molarity is you don't want to round, number one, and you probably want to carry extra digits. Whereas millimoles is less sensitive to rounding errors. And so if you do it my way, you're going to have step I. Step I is the initial step. Step I is equal to solution dilution. And solution dilution is going to be like this. We're going to take 10.00 milliliters of acid. And then we're going to add to this, actually, no, not 10, 20.00 milliliters of acetic acid. And then we're going to add to this plus 10.00 milliliters of sodium hydroxide that we're going to pour in there. And so that's going to give us a total volume of what? Now we're going to get a total volume of 30.00 milliliters. And so what we need to do is we need to calculate the new concentration of acetic acid and the new concentration of sodium hydroxide. So the concentration of the acetic acid it's going to be at 20.00 to 30.00 dilution of 0.100 molar. In other words, it's going to be 2/3 dilution, so it's going to come out to 0.066. We're allowed 3 sig figs here, but I'm not going to round anything. In fact, I'm going to carry extra. This just keeps going. All right, the sodium hydroxide, we're taking 10.00 and diluting it to 30.00. And this is going to be 0.100 molar. And so this is going to come out to 0.03333 bar. No, I'm not rounding it. And so these are my my new initials. Oops, I lost it here. All right, so I do this solution dilution at the beginning. Your book is going to do the dilution at the end. Okay, and now we can go on to step one. Step one is the strongest acid, which is acetic acid, plus the strongest base, which is sodium hydroxide. And then I'm going to plug in my initials. The initial of acetic acid is 0.06666 molar. And the initial of sodium hydroxide is 0.03333 molar. Which one's the limiting reagent? The sodium hydroxide. So that's going to go down to 0. And so we're going to lose minus 0.03333 molar here. And we're going to end up with 0.03333 molar here. And then the sodium acetate, we're going to end up with 0.03333 molar here. Step 2, we recognize this is a Henderson-Hasselbalch buffer, an HH buffer. If that's an HH buffer, then step 2 is very easy because I don't have to do the ice table. That is, the pH is equal to the pKa for acetic acid plus the log of the, in this case, the sodium acetate, which is the base, over the acetic acid concentration. If you look at it, the concentrations are the same, so this is going to be the log of 1. The log of 1 is 0. So an interesting thing happens. At the half equivalence point, the pH is equal to the pKa of the acid. This is at the half equivalence point. So this is one of the reasons why I wanted you to figure out what the pH is at the half equivalence point. Because if we figure out what the pH is at the half equivalence point, then we know that that's equal to the pKa of our acid. pH is equal to the pKa. The pKa of our acid we could look up in a pKa data table. It's kind of similar to a Ka data table. Okay. So let me pause it here. The x value is supposed to be 0.00134, not 0.0134. So when I did my K check, I used 0.00134, but when I did the pH, this pH kind of had me worried because the pH is, I mean, it's a weak acid, and the pH is kind of low for weak acid. But it was getting close to 2, so I just let it go. However, I used the wrong hydronium concentration for this pH. And so I want to correct that. And so this is 0.00134 molar, 0.00134 molar. I guess 0.00134 molar here. Actually, we don't want units there. It's going to be a order of magnitude off, and so it's going to be log of 0.00134 is 287, not 187. So let me correct that on my pH titration curve. The starting pH is going to be 287 here. All right, the pH of the half equivalence point, let's go ahead and finish that, is going to be equal to the pKa of acetic acid. Now the pKa of acetic acid is going to be the negative log of the Ka. The Ka for acetic acid is 1.8 times 10 to the minus 5. And so let's go ahead and take the log of 1.8 times 10 to the minus 5. It gives me 4744. And so in this case, the pKa is 4.744. So at 10 milliliters, I have a pH of this. Now, what I'd like you to do is I'd like you to calculate the quarter equivalence point so we can see, how this goes up. So can you go ahead and calculate the quarter equivalence point? And let me pause this. My recording here. Yeah, I forgot to resume the recording. There was an error here in the pH. I fixed it. I used 0.0134. I should have used 0.00134. So I corrected it here. But now we're calculating the quarter equivalence point at 5 milliliters. I'm going to do step I first. You got 0.08? And we're allowed 3 or 4 sig figs. I'll carry 1 extra. And the sodium hydroxide, you got? Yeah, that's right. Okay, then move on to step 1. And what is the K value for step 1? What is step 1? I lost my earlier work. I had step 1 here, but it's gone when Word crashed. So this is what you should have gotten for step 1. Here we start off with 0.08 thousand molar and we neutralize 1/4 of it, which would be 0.02 thousand. So we're left over with 3/4 left over. And that 1/4 that we neutralized was converted into product here. When we look at the product that's left over, we see that this is a Henderson-Hasselbalch buffer. A Henderson-Hasselbalch buffer doesn't have to have equal amounts of acid and base. In this case, it's lopsided. There's more acid than there is base, which alters the pH a little bit, but this is still a Henderson-Hasselbalch buffer because even though it's lopsided, I still have significant amounts of base. And so this is an HH buffer. So for step 2, it's pretty easy. What do we use? We use the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is the pH depends on pKa, which is a constant, plus the log of this ratio. The ratio is going to be the ratio of acetate, or sodium acetate, the base, over the acid. And I don't have to make up an ice table because these are the initials for step 2. So the equilibrium from step 1 goes to the initials of step 2, and that's what I plug in here. And so this is 4.744 plus the log of the base, 0.02, over the acid, 0.06, or the log of 1/3. What is the log of 1/3? The log of 1/3 comes out negative. And so log of 1 divided by 3, negative 0.477. 477. Plus 4.744 gives me a pH of 4.266. 4.266, or 4.27. So at the 1/4 equivalence point, my graph disappeared too. I have a pH of 4.87, or not 4.87, what was it? Sorry, 4.26. 4.26. Here. And then at the half equivalence point, I have a pH of 4.74. What did you get? 4.283. Yeah. That's quite a bit off. 4.74. What did you get for your log of 1/3? Or
Well, it's negative 0.477, so 4.76 minus 0.477.
4.76? Maybe my writing's too off. It's 4.74. Yeah, this is supposed to be 4.744. So recalculate it. Okay, so we're starting to map out the titration curve here, you know. So I start off at 287, I jump up to 426 here, and then I jump up again to 474. But what I'm going to do is I want to get some more points in here. And so this is the long way of doing it. And we have another name for this region of the curve. I called this region the excess acid region. This excess acid region is called the buffer region because of step 2. And it turns out this is the easiest way to make a buffer. Let's say I want to calibrate my pH meter. I want to make a pH 4 buffer. Do you know the easiest way to make a pH 4 buffer? Get some acetic acid. Get some sodium hydroxide, and then just add the sodium hydroxide until the pH gets to 4 and stop. Once the pH gets to 4, then you just made a pH 4 buffer. Buffers have interesting properties because buffers are a mixture of weak acid and weak base. You know, when you have a weak acid plus a weak base, what's the K for that? It's not very large, it's not very, very large, it's not very, very, very large. The Ka is very small for that. And so the weak acid and weak base form a stable mixture. When we have a weak acid and weak base that form a stable mixture, then the buffer, the reason they call it a buffer is you can add strong acid to it or strong base to it and the pH stays relatively flat. And so look at, let's say I have my buffer here with a pH of about 4. You know, if I wanted a buffer, I could calculate how many milliliters it would take to get to pH 4. Let's do that. I'll do it the long way, and then we'll do it the short way. So I don't want 474 or 426. I want a pH of 4. Actually, before I do this, let me show you the shortcut way of doing this. One of the properties of a buffer is a buffer only depends on the ratio. If we only have the ratio and the acid and the base are in the same container, then solution dilution does not change the ratio. Solution dilution does not change the ratio. The reason is because both the numerator and the denominator would have the same dilution factor. So let's say you had a 1:2 dilution of the base. If you had a 1:2 dilution of the base, that means you had a 1:2 dilution of the acid. So you have 1/2 over 1/2, which is just 1. And so solution dilution does not impact it. Since solution dilution does not impact it, we have a nice shortcut method for determining the pH. And the nice shortcut method it goes like this. We take the pH is equal to the pKa plus the log of the equivalence point over the remaining. What I mean by that is this equation comes out to the pKa plus the log of some kind of equivalence point. It could be the whatever over whatever. And so I'll just say x over y, equivalence point, over the remaining. The remaining is going to be this. It's going to be y minus x over y. Y over y minus x over y. It'd probably be easier just to think in this way. Here. One way of thinking about this is, let me give you an example. The pH of the half equivalence point. The pH of the half equivalence point is equal to pKa plus the log of, okay, what I did was I converted 1/2 of my acid into conjugate base, and that means I have 1/2 left over. So this is going to be 2 over 2 minus 1/2. And so this is going to be pKa plus the log of 1/2 product, 1/2 unreacted reactant. So 1/2 product and 1/2 of the reactant remains. A log over 1/2, 1/2 is log of 1, therefore the pH is equal to pKa at the half equivalence point. The next example is the one we just did, the 1/4 equivalence point. And so I go straight to the Henderson-Hasselbalch. I'm in the buffer region. pH is equal to pKa plus the log. So if I'm at the 1/4 equivalence point, I've converted 1/4 of my acid into base. And so I have 1/4 base, And then I have, well, I had 4/4, and I've neutralized 1/4. So how much do I have remaining? I only have 3/4 remaining. So this is equal to pKa plus the log of 1/4 over 3/4, which is equal to the pKa plus the log of 1/3. Well, the log of 1/3 is minus 0.477. So at the 1/4 equivalence point, it's just going to be pKa minus 0.477. So at the 1/4 equivalence point, it's just equal to the pKa minus 0.477. We'll do the next example. The next example is at the 3/4 equivalence point. At the 3/4 equivalence point, then the pH is equal to the pKa plus the log. So if I neutralize 3/4 of my acid, then that gets converted into product, base here. So it's going to be 3/4 base, and then how much do I have left over unreacted? I only have 1/4 left unreacted. And so what that gives me is it gives me pKa plus the log of 3/1. The log of 3/1 is just the opposite sign of the log of 1/3. So this is equal to the pKa plus 0.477. So I just add it rather than subtract it. Well, if I add it, then I'll take my pKa, which is 4.744, plus 0.477, and that gives me 5.22. So at the 3/4 equivalence point, which is here, I'm going to be at 5.22. And then I usually do two more. I do two more because they're easy. And they also have a secondary significance. The two more I like to do is, I like to do the 1/11th equivalence point. Now, what does the 1/11th equivalent point, how many milliliters does it come in at? So the 1/4 equivalence point came in at 5 milliliters. .00 milliliters. What does the 1/11th equivalence point come in at? How many milliliters? So you take your 20 and you divide it into 11 parts. So just 20 divided by 11, and it's going to come in at 1.81 milliliters. And you might think, 1.81 milliliters, why am I doing it there? Because it seems like an odd number. And the reason I'm doing it there is not because of the milliliters. The reason I'm doing it there is because of the base to acid ratio, which is important. And so at the 1/11th equivalence point, I'll do it the shortcut method, which is the pH is equal to pKa plus the log. So I've neutralized only one part out of 11. If I've only neutralized one part out of 11, then I've converted 1/11th of it into product. That means I have 10/11ths left over, correct? And so why I picked the 1/11th is because of the ratio. Take a look at the ratio of base to acid. It's going to be a 1 part base to 10 parts acid. Do you see that? And this gives us a nice clean number, because what is the log base 10 of 1/10? It's -1. And so that's easy. It's pKa -1. pKa -1 is quite easy. So at 1.81 milliliters, I'm going to have 474 minus 1 is 374. And then I like to do the 10/11th equivalence point. And so at 10/11ths, what do you think it is? We just flip the ratio. And so at the 10/11ths, it's going to be 10 parts of base to 1 part of acid. And so at the 10/11ths, I'm sorry? Yeah. exactly. pKa plus the log of, okay, so we converted 10/11ths of our acid into base. That means that there's only 1/11th left over. And we can cancel out the 11ths and we'll get pKa plus the log of 10 to 1. And so it's 10 parts base, 1 part acid. When we have 10 parts base, 1 part acid, then the pH is equal to pKa plus 1. And so it's just 574. And so at the 10/11th, how many milliliters does it take to get to the 10/11ths equivalence point? Well, 20 milliliters is 11/11ths. And so we could figure it out. We just take 10 times 20 divided by 11. That gives me 18.18 milliliters. This is 1.818 milliliters. I didn't round it correctly. All right, so these points are very fast using the shortcut method. All these points are very fast. And we can take advantage because it's in the buffer region. In the buffer region, do we have to do solution dilution? No, because buffers have a unique property that their pH doesn't change with solution dilution unless you overly dilute them. If you overly dilute them, they'll change. The other way we could do this is you can just pick milliliters. Alternatively, pick milliliters. Oh, pages here. I'm going to go to new document, otherwise it's going to crash. So let's say at 8 milliliters, 8.00 milliliters of base. Then the pH is equal to pKa plus the log. Now I've neutralized 8 out of 20, so I'm going to call it 8 out of 20 have been neutralized to product. That leaves 12 out of 20 left. This top term here is what I call the equivalence point. And so this is the 8/20ths equivalence point. (8/20ths equivalence point comes at 8 milliliters, 8/20ths times 20. Does that make sense? For that. And so these are shortcuts. Now, what we're going to do is, I don't want these odd numbered buffers. I want a buffer that's pH 4. And so this is the second type of calculation we're going to do. We're going to do it the long way and the short way. So what the question is if we want a pH equal to 4.00, how many milliliters of sodium hydroxide will be required to hit that pH? And so if we do it the long way, then we're going to use the ice table to do this. But when we do the ice table, we're going to kind of work backwards in doing this. And so how do we do that? How we do that is, okay, I'm going to start at step 2 and then work backwards. So if we start at step 2 says the pH is 4.00. Well, step 2 says that's equal to the pKa plus the log of the ratio. The pKa is 4.74. 4. And so what we're going to get is we're going to get the log of the ratio is equal to 4 minus 4.74, which is minus 0.744. And then we're going to take the anti-log of both sides. And so the ratio of base to acid is equal to 10 to the minus 0.744. And so I'll take the anti-log of minus 0.744. And comes out to 0.1803. So I need the base to acid ratio of 0.1803 to 1. So then I'm going to go back to step 1, and that's my final ratio. So I'm going to have my HAC plus NaOH, and this is going to yield NaAC plus H2O. So I'm working backwards here. So I'm going to have 1 part of acid and 0.1803 parts of base. Then I have to work backwards. So can you fill in the rest of the table for me? I just need this ratio.
Can you go up a little bit?
I forgot to resume my recording. Shoot. So just to summarize here, I'll save some time and not do the algebra here, but it becomes a pretty straightforward problem. And so as an alternate to working backwards, we work forward. So we work forward, but we have unknowns here. And so we work forward, we generate the equations. Once we generate the equations, then we can solve for the original unknown. Does that make sense? Here? Okay. And so we could do this. This is especially critical. In the buffer region, we don't have to do this. But if we're outside the buffer region, we have to do this because we have to factor in solution dilution. In the buffer region, this is very easy. So this is the long way, but you could use the long way for all your calculations. You can't use this shortcut for all your calculations. This shortcut only works in the buffer region. And a lot of people try to use the shortcut method for all regions. You can't do that. And so the shortcut method is we need this buffer with a pH of 4.00. That's going to equal the pKa, which is 4.74, plus the log of our ratio. And so then we calculate our ratio here. And once we calculate our ratio comes out to what was it, 0.1803? Yeah, 0.1803. Here. Okay, so what I do is this. that ratio is equal to 0.1803 parts of base to 1 part of acid, correct? And then I need to do one other thing. The next step here is I'm going to do this. That means I've neutralized 0.1803 out of the total. What was the total? What we have to do is we have to add these two. And so it's a total of 1.1803 over how much is left unreacted, 1 part out of 1.1803. So this is going to give me the ratio of 0.1803 over 1. Okay. But we call this the equivalence point here in the numerator because that's how much I've neutralized. So what that means is I'm at the 0.1803 out of the 1.1803 equivalence point. How many milliliters is that? Well, how many milliliters that is we just multiply that by 20. So this 0.1803 divided by 1.1803 times 20.00 milliliters, which is our full equivalence point. And so 0.1803 divided by 1.1803 times 20. And that means at 3.055 milliliters of sodium hydroxide, I should hit pH 4. So again, this only works because we're in the buffer region. And this is the tricky part here. I have to go from a base to acid ratio to equivalence point. The equivalence point is how much acid I've neutralized versus how much remains. And so this is the fraction neutralized, this is the fraction remaining. And how I get the denominator is I just add the base and the acid together. Okay, is that clear for that? All right, so I talked about that. And so these calculations in the buffer region are quite quick. You can do this fast because we can skip the solution dilution. But once we go outside, like for example the equivalence point, we have to worry about solution dilution, and the excess base, we have to worry about solution dilution. And the excess base calculation is something similar to that, but I'm going to stop talking about the titrations. I'll talk more about buffers since we're in this buffer region tomorrow. So we should get the same, 3.055 milliliters if I use the algebra to solve this here. Get the same. All right, I used up some of the lab time to catch up here and talk about the pH titration. But this lab is long, and so I'll probably shorten it, but normally I have the students run a bunch of unknowns, but we'll cut down the number of unknowns to save some time. But this is qualitative analysis. This is the same type of qualitative analysis you've done probably in Chem 4, but it is quite a lengthy procedure. And so I wanted to talk about prepping for this. You'll probably want to prep for this to make the lab go more smoothly. And so you'll just kind of read through the intro part here, and then we get to the procedure. And this is the way I would probably set it up. I would probably make a small copy of this and put it into my book. And then what I do is I'd talk about, our unknown contains these potential cations, sodium, ammonium, etc. Oops, that's not what I wanted here. Has everyone done qualitative analysis before? Okay. And so we're just going to use chemical tests to determine what's present. And so to speed things up, I would either copy this by hand or copy it and tape it or paste it or glue it into my notebook. And so the first thing is all these are aqueous. And so how many milliliters of unknown do we need? Now what we're going to do for part one is we're going to run a known, not an unknown. You could run your known and unknown side by side, but we're not going to do that. We're going to just run the known and see, all the steps should work out here as positive. And so, how many milliliters of known do we need? Do you know? And so then you'd have to go back and read through the procedure, and it takes a lot of time. And so what I do is I just do some pre-prep for this. And so probably on Monday you'll want to pre-prep. Do a little, take a look. So here we're talking about the ions. Let's scroll down. Let's find the procedure here. Okay, there are multiple flow charts here. This is all theory. Okay, now we're at the procedure. So the initial observations and tests for sodium and ammonium. Number 1 is very fast. It doesn't take much time. So don't start with number 1. I would finish with number 1 because those are individual tests. Those aren't part of a long flow chart. However, separation and detection of silver is the start of the long flow chart. And so here it says 10 drops of the original solution to be analyzed in a small test tube. Add 5 drops of distilled water and 2 drops of 6 molar HCl. What's easier to detect? More concentrated or less concentrated solutions? Is it easier to detect if you get more precipitate, or is it easier to detect if you get less precipitate? More. And so what we're going to do here is, we're going to put 10 drops of original solution in there, but we're not going to add 5 drops of distilled water. Why add water? Because all you're doing is solution to dilution. And when you do solution to dilution, you're going to get lower concentrations. And lower concentrations means it's harder to detect. So I'd just rather do 10 drops of original unknown solution and then add 2 drops of 6 molar HCl, maybe. Stir well, centrifuge, reserve, decant, wash the precipitate here. However, the problem with this procedure is written for all unknowns. And some unknowns are more concentrated, some unknowns are less concentrated, right? This is just written for your generic unknown, which might not work very well. So do we want to take a one-size-fits-all approach to this lab? We don't want to take a one-size-fits-all approach. And so what we're trying to do here is this. Here. So the way I'd prep this is I'd go through and I'd look at the mounts and the concentrations. And so I would just write 10 drops here. And the preliminary, number 1, I skip that because those are preliminary, those are separate from the flow chart. I want to jump into the flow chart, which is number 2 here. The first part of number 2 is we want to precipitate out the silver as silver chloride. None of the other cations in there will precipitate out as a chloride. The only insoluble chloride is silver. And so what our goal is we want a complete and clean separation of silver ions. Is 2 drops enough? Maybe, maybe not. The problem is it's generic. It's written for. And so what happens is sometimes 2 drops is not enough. If 2 drops is not enough, you know what happens? You don't precipitate out all the silver. If you don't precipitate out all the silver, then silver gets trapped over here. If silver gets trapped over here, it screws up all your colors and everything. And you're going to come up to me and ask me, what's going on? It's supposed to be a white precipitate. I'm getting a brown precipitate here. I don't know what's going on or what happened. It's probably because you didn't have a clean separation. And so in order to get a clean separation, the drops I put the concentration of the HCl. The HCl is 6 molar. So we're using 6 molar HCl. How many drops? I'm going to add as many drops as it takes to get all the precipitate out. So if it takes 10 drops and the procedure says to use 2 drops, I'm going to use 10 drops because I want all the silver out of there so it doesn't contaminate the rest of my procedure and screw up all my precipitates. If silver gets over here, you're screwed, basically. And you're going to be there and you're going to waste so much time thinking, oh, what does that mean? Do I have this or don't I have this? So, in other words, we want to clean and it goes both ways. So let's say I precipitated out all the silver. How do I know I precipitated out all the silver? What you do is you wait for the silver chloride to settle, and then you get a clear supernatant solution. The supernatant solution is liquid, and then you add another drop of HCl. When that drop of HCl hits the supernatant and you see more cloudiness develop, then you know you're not done. But the problem is it takes a long time for this cloudy suspension to settle. So we don't wait. What we're going to do is we're going to throw it in the centrifuge and get it to compact down. And so immediately when it gets too cloudy to see anything, it's too cloudy. I can't tell if I'm getting more clouds or not. So what you're going to do is throw it in the centrifuge, spin it down. It's going to compact it into a nice compact pellet at the bottom, and then you're going to add another drop of HCl. If it comes out clear, you've precipitated out everything. If it comes out cloudy, keep going, regardless of the number of drops. And so I don't say 2 drops, I just say 6 molar HCl and complete the precipitation. So what we're going to do is we're going to centrifuge down the precipitate here, or we might filter it. I think, what are we doing? Are we going to filter it or centrifuge it down? Let's take a look at the procedure. So I'm skipping number 1, I'm going straight to number 2 here. Centrifuge and reserve the decantate. Okay, we're not going to filter this. The way we're going to separate the solid from the liquid is by decanting. Do you know what decanting is? You're going to centrifuge the precipitate down into a pellet at the bottom of the test tube, and then you're going to take the liquid and pour it into another test tube. Are you going to get 100%? You're not going to get 100% of the liquid because we don't want any precipitate to cross over. If precipitate crosses over, that's a problem. But we don't want to lose any solution because the more solution we lose, then the less future precipitates we're going to generate. And so what we don't want to do is we don't want to lose a lot of the aqueous ions with the precipitate because that's going to screw up the next test here. Let me show you what the next test is. So this is the general here, separations. And then let's take a look at the next test here. So we get our white precipitate, but our white precipitate is contaminated with decantate solution. And so what we're going to do here is we're going to wash it. So we'll take our silver chloride, wash it, centrifuge it, and then pour the rinse into the decantate solution. That way we don't lose any of these ions. And then So the first wash we're going to pour over here. The second wash we're probably going to throw away because we don't want solution dilution. Too much solution dilution means you're going to be switching from test tubes to 500 milliliter beakers by the end of this, because you're going to just have way too much. We want to keep it in test tubes the whole way through. So we don't want too much solution dilution. So the first wash for sure we're going to combine because that's going to contain a lot of the decantate ions. The second wash we might combine also, but if we did a third wash, we would throw it away, discard it. That's to prevent over dilution of the decantate. Okay, once we have our clean, we need a complete and clean separation. That's the clean part. The clean part is this white precipitate should be fairly pure. Now, if we have a white precipitate that's fairly pure and we add ammonia to it, then the precipitate will dissolve. Now, how much ammonia do I add? The book says add this many drops of ammonia, and then watch the pH. I don't even pay attention to that. You know what I want to do? I want to dissolve all my precipitate by complexing it. And so how much ammonia do I use? I use a minimum amount to dissolve all my precipitate. So I'll add a drop, stir it, add a drop, stir it, add a drop, stir it. And once all of it dissolves, that's how much I need. This is how you can customize the procedure to fit your unknown. Otherwise, if you're using the book's procedure, it's going to screw things up. Does that make sense, Mona? I mean, this is what I mean by modifications here. And so how much do you add? Don't add the amount the book says because oftentimes that's overkill. That's way too much. And if you add way too much ammonia, you have to add way too much HNO3, and you might not get this, what we're looking for. And so we're going to add the minimum amount of ammonia to dissolve all that. Once we have it all dissolved, then we're going to reprecipitate it out by using HNO3. Just drop by drop until we see the precipitate come out again. Or there's no precipitate, maybe. If there's no precipitate, just make sure you have it acidic enough. And so here, we might have been too conservative. And so one way to test it is to use litmus paper. HNO3, ammonia is a base, so this is basic. HNO3 is an acid. Acids turn blue litmus red. Bases turn red litmus blue. So acids are red. This is another reason why the physicists who did the electrostatic potential maps don't do enough chemistry or didn't do enough chemistry because, in the electrostatic potential maps, the acids are blue, but in litmus, acids are red. But anyway, going back to this, we can just test this solution with, this is why they're telling you to test it, just in case you're too conservative with the acid. Just keep adding. For me, I just keep adding the acid, and then well, this is total overkill. Volumes increase in weight, and I'm not getting any white precipitate. But once we get a white precipitate here, then this is a positive test for silver ions in our original solution. And so we have these separation steps that were up here are critical to have good results. And so what's the next key separation? The next key separation is to separate the iron, chromium, and aluminum as solid hydroxides by adding ammonia, ammonium chloride. This is a buffered solution. This is a buffered solution because it's a weak base and a weak acid combined together. That weak base and weak acid is going to limit the amount of hydroxide. So we're adjusting the pH, which in turn adjusts the pOH, because we don't want all the hydroxides to precipitate. What are the other hydroxides that can precipitate? The other hydroxides that can precipitate are magnesium, nickel, and zinc. Magnesium and nickel and zinc, those are +2 cations. Whereas iron, chromium, and aluminum are +3 cations. +3 cations are more reactive than +2. So what we're doing is we're trying to adjust the amount of hydroxide in there so only the +3 hydroxides precipitate, leaving the +2 hydroxides in solution. Does that make sense? So here you have to follow their procedure for making the buffer. Their procedure for making the buffer is to, dump in ammonia and then add ammonium until the pH, until litmus turns a color. I think blue litmus turns red. Something like that. And so this is making a buffer. There are different ways we can make buffers. So this is making a crude quick buffer that controls the pH, which controls the pOH, which controls the hydroxide level. We don't want the hydroxide level to get too high, otherwise we're going to precipitate magnesium, nickel, and zinc. So this is a crucial separation here. You got to be careful with this. But anyway, once we form the precipitate, we'll wash the precipitate. The first wash goes into the decantate. Probably the second and third wash we can discard. Okay, then we'll further analyze these over here. And so the amounts you usually do based on what you're trying to do. If you're trying to do a precipitation, you use as much as it takes. If you're trying to dissolve a solid, you use as much as it takes. However, something like this buffer, I would write down the amounts here, because that's a little more tricky. But even writing down the amounts, they tell you to adjust it on the fly. So that's essentially it. So what we want to do is we want to prep for 2, etc., 3. We're just going to do this in parts. I don't know how far you're going to get on day 1. Day 1 will be on Monday, so come prepared to start day 1. Eventually we're going to go through the entire flow chart. And once we go through the entire flow chart and we have some observations, the observations make sense, then we're going to run our unknown. And you're going to get at least one unknown for the cation flow chart here. And then we have some anions as well. All right. All right, are there any questions? All right, that's enough talking for today, I think. What I'd like you to do, though, is I'd like you to look at your acid and tell me what the pKa of your unknown acid is. Now, if you have a diprotic acid, the first half equivalence point is pKa1. The second half equivalence point is pKa2. So we want to figure out the pKa's of our acid. Let me know if you need help with that. Otherwise, we'll just call it a day.